don't forget that you actually have, you know, 2 nitrogens there. And then over here, you have to recognize that you actually have oxygen in 2 places. So we started with 3 oxygens. So I would start with trying to fix my hydrogens. I have 4 on the reactant side. If I want 4 on the product side, let's start there. So I'll go to red here. I'll put a 4 there in front of my H2O, and that will bump, wait a minute, oops, I don't want a 4 there. How about a 2? I'm going to put a 2 there. That feels better. So now that bumps my hydrogens up to 4, and now my oxygens are 4 also. I have 2 for my O2, and I have 2 for my H2O. Well, then it just looks like my oxygens are messed up. But they are very messed up because I need more oxygens on the reactant side, so I'm going to try putting if I put a 2 there, that will give me, what, 6 oxygens? But that's not going to get me down the road for, 6 oxygens. Yeah, I'll try that. I haven't done this one, as you can see. So I'm going to try a 2 here, and that will give me 6 oxygens. And nitrogens, now I have 4, and hydrogens I have 8. Direct. Okay then. Kind of chasing our tail here. So if I wanted to fix my hydrogens over on the product side, so I have 8 on the reactant side, looks like I need to go with a 4 here. Okay, so if I go with a 4 there, that gives me 8. And now now my oxygens, I have 4, 5, 6. 6. That's looking pretty good. Now I can see the light at the end of the tunnel. So now my nitrogens, I have 4 on the reactant side, and I only have 2 on the product side. But I can get 4 if I put a 2 right here. Okay, so it's definitely kind of going back and forth. So if we double check that we have the same number of everything, nitrogens, hydrogens, and oxygens, it all matches up. Is that what you got? So this was a good example of going back and forth. Any questions about that? So on your week from Thursday is your exam for this material. You'll definitely have some chemical equations to balance. All right, on with new stuff, but not too new. Whenever you do a calculation where you're going from, I'll write it this way. So a reaction, we go reactants to products, and we go ahead and write an equation, reactants to products. If you're given the amount, you know, grams or moles of the reactant, and you're trying to get grams or moles of a product, that is what we call a theoretical yield. That's a theoretical yield. It just means, the word theory means, well, in theory, it's what it should be. Okay, so what you think you should get, that's a theoretical yield. And it says upper limit, and actually, we usually don't get back in the lab or in real time what we think we're going to get back. Usually our yields are low, okay? And you might already figure out why they're low, but I'm going to kind of add to that. One reason they're low is, oh, you screwed up. One reason they might be low is, oh, you lost some of your product, like when we were doing the copper experiment, okay? But here's another reason why, these are all reasons why they might be low. In chemistry or chemical reactions, there's this thing called reaction kinetics. The word kinetics in this sense means how fast it occurs, okay? So in other words, it's possible that it occurs too slowly that you don't wait long enough for the reaction to occur. Here's another one. This is pretty common in chemical reactions. We've been doing like a one-way arrow. We've been saying reactant or R, reactant goes to form P, reactant goes to form product. But, and I have an example of one coming up here in a minute, it's possible that it goes not just one direction, but it also goes backwards. So this is what we call an equilibrium. It goes from left to right and also goes from right back to left again. So you're never going to entirely get products. Another reason is that, and I think we ran into this when you guys did your magnesium, you burned it and you reacted it with oxygen in the air. In the background information it said an unwanted chemical reaction with magnesium in that case was it combines with nitrogen, not oxygen. So in that case, you kind of, it goes off on a tangent, goes off on a side reaction, and you're like, you're not going to get your product back. Your yield is going to be low. And then another one is physical losses. I think I might have a slide to talk about what gross errors are. Physical losses are what we say inherent, or just they have to be part of the experiment. Physical losses, you can't do anything about these. A gross error would be like you spilt your reaction material. Okay, so those four. So I have a slide to kind of talk about each one of them. The word reaction kinetics in chemistry talks about how quickly a reaction occurs, and like I said, if it occurs so slowly that there's no way you can practically wait for it to proceed to go completely, then when you pull your product, it's going to be low. That makes sense. So for instance, this is showing you reaction kinetics. Along the x-axis, we haven't done a lot with graphs here, but along the x-axis we have time, and along the y-axis we have concentration. And the red one is reactants, and the green one is products. So basically, over time, the reactants decrease and the products increase. So it's kind of cool. So all this says is if you pick, and the example here is 7 seconds. So let's see, these go by increments of 2, so that's, this is 6, so 7 here. If you pick 7 seconds, okay, what it's saying is basically only half of your reactant is converted and only half of your product has been formed. Okay, so that's kind of what that means. Your yield will be low. Chemical equilibrium, that's the two-way reaction arrow. We're in Gen Chem 2 right now, we're studying acid-base chemistry, and oh my gosh, that's definitely a two-way arrow. Okay, to understand the whole pHs and things like that. So the example I have here is a chemical system in equilibrium. So of course we have H is hydrogen, I is iodine. We talked about the fact that in nature those are diatomic. So we have H2 and I2 reacting to form HI. Okay. And it's a balanced equation. But notice that it not only goes from left to right, but it also goes from right back to left again. And so that again, if we look at kind of how it proceeds, this is time. What they said is that you started out with all of the H2I2 and none of this. Again, along the along the x-axis is, along the y-axis is concentration. So basically this is 0. So what they're saying is, given some time, of course your reactants will decrease, but notice they won't go to 0. They'll kind of steady out. This is what we call equilibrium concentrations. Equilibrium concentrations. So actually, I don't know where it would be, but kind of somewhere in here where they leveled off, those are equilibrium concentrations. So you're not going to get all the product because some of the product goes back to form reactants again. And it's a dynamic equilibrium, which is kind of cool because my mom even thinks it's cool. It kind of keeps going back and forth and back and forth. So the next one is the side reactions, and I think I did the example of magnesium not reacting with oxygen like we wanted to, but also reacting with nitrogen. So you're just kind of out of luck when that happens. And physical losses. Now again, these are physical losses inherent to the experiment. So, yeah. I think of pharmaceuticals. Like if you are into pharmaceuticals, you know that the stuff you ingest needs to be especially pure. And not only pure, but its concentration needs to be very well known. So I guess let's go together. The more you purify something, there's different, in chemistry, there's different ways of getting something more and more pure. The more you purify it, the more you lose. So there's a trade-off to going through these different purification steps and losing your product. Okay, so when we write so many grams of reactant will give you so many grams of product, that's in a perfect situation. Okay, that's assuming that all of your, the reactant of interest, which is your limited supply reactant, I'll talk about that here in a minute, your limited supply reactant reacts. That's assuming that you don't get any side reactions. And that's assuming that when your product is formed, you can go ahead and find it again. Okay, so a lot of times on paper and pencil, the grams you think you're supposed to get are not the grams that you get back. So gross error, what is gross error? Gross is what I call the oops error. So gross is not inherent or just part of the experiment. Gross error is the experimenter did something wrong. And they include things like spilling your reaction solution. You could you could misread a measuring device. You could mess up your calculations. You could not follow instructions. Those are all gross errors. It's the oops errors. And you guys have done really well this semester. Very few oops errors. So this kind of last part of the slides, I call it a lot of blada blada. It's important, cool blada blada. But the wordy part, remember on the unit exams, I usually have a section where I ask, the first sections before the problems, where I ask stuff about definitions and stuff. So you might want to make sure you look at these. Okay, so now we're on to one other type of calculation related to theoretical yield, okay, and actual yield. So it's called percent yield, and it's just a division. It's a relative amount of what you got back in the top, what your actual yield is in the top, divided by what you thought you should have gotten back, your theoretical yield in the bottom. So theoretical yield, just to make sure we're all on the same page, I'll go ahead and say theoretical yield. You get that usually, although you have a couple of problems to work for Wednesday, you usually get from stoichiometric calculations. Usually from Stoich Calc. So what you should have gotten back. Now, I'm pretty sure I know which lab that I want y'all to do on Thursday, and you guys will be doing percent yield calculations. And then the top is, sometimes I'll call it experimental yield. It's what you really got back. And usually your experimental yield is low. I'll say usually low. And it's usually low for the reasons we just talked about a few slides ago. And usually it's grams you got back divided by grams you thought you should have gotten back, but it could be moles that you got back divided by the moles that you thought you should have gotten back. And to get it into parts per 100, we multiply by 100%. So let's do an example. Now, we're not going to do the stoichiometric calculation because we already did. So last week, I guess it was probably Friday, we said that if you have 1.25 grams of Cl2 and you have sufficient, I think I probably put enough, but if you have sufficient, excuse me, P4, we did a calculation that said that the amount of PCl3 you get back should be 1.61 grams. That is the theoretical calculation. That's a theoretical yield. Okay, so that's a theoretical yield. Let's just say you go to the lab, you have your 1.25 grams of Cl2, you have sufficient P4, and instead of getting 1.61 grams back, let's say you get 100.08 grams of PCl3. So it's low, and you thought it would be. Okay, so calculating the percent yield then is simply a ratio, a division. So we put what we got back, which is 1.08 grams, divided by what we thought we should have gotten back from the stoichiometric calculation, 1.61 grams. We take that and we multiply it by 100% and round to 3 significant figures, and you get 67.1%. So those are percent yield problems. So let's take a look at these, and after all the other stuff you guys have been doing, this is like cake. Okay, so these two will be due on Wednesday. So the blue, of course, is the answers in the back of your book, but check it out. So it basically says if the theoretical yield of a reaction is 24.8 grams, theoretical yield goes in the bottom, and what you get back, actual yield, is 18.5 grams, that'll go on the top. What is your percent yield? So it's just a division problem. And the other one is similar. But I'll warn you that usually those theoretical yields you get from stoichiometric calculations. In this case, they're just giving it to you. Okay, giving it away. Okay, so let's finish out this part talking about one other topic that I'm not going to go into, do any sort of necessarily calculations. But, and this makes sense to you, I bet. Sometimes when you have your reactants that are going to react together, more than not, you're going to run out of one reactant before you run out of the other one. The one you run out of first actually is called your limited reactant. Okay, that's it. And in general chemistry, we do more with this, but in order to do a stoichiometric calculation, you have to know which one you're going to run out of first. So for instance, we'll go back to the baking brownies. Let's say you wanted to make as many brownies as possible, and you went to your cupboard, or as many batches of brownies as possible, and you went to your cupboard and, let's see, let's pick on the eggs. Okay, we had a half a dozen. Wait, no, let's make a dozen. So we have 12 eggs. So I can make 3 batches there, right? And with regard to brown sugar, though, we only had 2 cups. Okay, so I could make 3 batches with my eggs, but how many batches could I make with my brown sugar? Only 2. So not looking at all the other ones, but in this case, can you see where my brown sugar is in limited supply? It's the limited reactant. And it drives how many batches I can make. So that's it. That's all it is. So kind of along those lines, we're going to look at if you were making sandwiches and for every sandwich you put a piece of bread on top, a piece of bread on bottom, and you had a piece of ham in between them. So we kind of have stoichiometric coefficients of 2, 1, and 1, respectively. Okay, if we kind of think through this situation, if we have 20 slices of bread, I'll put have 20, and we have 7 slices of ham. Have 7 slices of ham. So, how many sandwiches can we make? 7. Why? That's right. We can only make 7 because if we tried to go ahead and use up all our bread, we'd make 10, but we run out of ham before that. Exactly. So our ham is limited. You got it. So when we're done making sandwiches, how many slices of bread are left over? So we had 20. We began with 20. Yep. We had 20, and we're going to use 7 times 2. We're going to use 14. We're going to have 6 slices left. 6 bread left over. So we use the word limited supply for the ham, and we use the word excess for the bread. So the bread is in excess. In the previous example with the brownies, the eggs were in excess. Yep, that's it. So switching gears to a regular chemical reaction where 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. I have this little video to kind of show you if we have 6 molecules or moles of N2 and 12 molecules or moles of H2. And I would have to do a little. And again, in Gen Chem 1, we talk about how can you use math to figure out which one you're going to run out of first. But even though we're not going to do calculations, I want you to understand the concept of a limited reactant. It's the one that you're going to run out of first and the one that governs how much product's going to be made. Okay, so for the problems we did up to this point, you did not have to identify the limited supply reactant. So that's actually, those are called ordinary stoichiometric calculations. And so that's the type that I'm holding you responsible for. Okay? All right then. Very good. We'll see you on Wednesday. And Wednesday we're definitely going to start on solution